All right.
Okay. A technical note is that I only have one screen, so I can't see what you're doing. So if anyone wants to interrupt me for some reason, you have to do it audibly, or I won't see your interruption. Here I'm sharing the screen. And let's begin. Hello, everyone. My name is Dmitry Khalansky, and I'd like to give you a quick look at the IRIS framework. First, why should you listen to me specifically? What knowledge do I have about the IRIS framework? We and IRIS, we go a long way. About 2 years ago, more than 2 years ago, when I joined JetBrains as an intern, I was tasked with proving the correctness of some concurrent algorithm. It doesn't really matter which one. The task was really open-ended, and I was only given this task because I already had some experience with the proving systems. After having a look at the proving systems that could possibly deal with concurrent algorithms, I decided to use IRIS, and without basically any supervision, without much guidance, only having the authors of the IRIS framework in their Slack channel as people who could give me some advice, I nonetheless managed to prove the data structures that I needed. I managed to do it twice because the data structure was reworked once. Each time the work I did amounted to about 10,000 lines of code. Some of the things that I did were contributed back to the IRIS framework itself. If you'd like to take a look at my proofs for some reason, you can find them under this link. During that year, I did have to dive deep down into the internals of IRIS to make sense of what's happening, as it is an extremely experimental thing yet, not really the industry standard. For the introduction, I have prepared some slides about what Hoare triples are, and I suppose everyone already knows about them. I did list them as a prerequisite. If everyone is comfortable, I will be skipping ahead. Just note that we'll be using this syntax, and that the Hoare triples we are dealing with don't claim that the execution will eventually finish. Hoare triples, as far as I could see, never do, because preconditions sometimes do. Here we have a quick motivating example of proving a quicksort algorithm using the Hoare triples with inline annotations between lines of code. Again, if you do know what Hoare triples are, there's nothing fancy here. Everything is as you would expect. Just something that I want to direct your attention to is the fact that every line has this logical statement listed. And this logical statement basically means that the quicksort implementation provided here does not touch any array elements other than those between the pointers low and high. Otherwise, the proof wouldn't work because this quicksort helper recursive call could potentially mess up the already sorted part that was sorted by this recursive call. And most of you probably already know where I'm going with this. Separation logic allows us to get rid of this ugly statement that propagates through the whole proof. But separation logic has another important property besides allowing us to get rid of this thing. Specifically, I'm talking about the fact that separation logic can be concurrent and allows us to deal with some concurrency problems elegantly. Here's another implementation of quicksort that launches some calculations in parallel with the main thread. So in the main thread, we have one recursive call of quicksort, and then we wait until the other recursive call that is running in parallel finishes. The spawned thread indicates that it has finished by setting the finished variable to true. Is everyone comfortable with this definition of quicksort? Okay. The problem is we can't use just simple Hort triples without separation logic to prove this function using this spec. Why can't we do that? Because here's a counterexample. A quicksort helper that for some reason messes up the order of some array elements that it shouldn't have any access to. And then to make the specification work, it swaps them back. So we would think that this function satisfies this specification, but if so, then its concurrent version that forks the recursive call is certainly not valid due to some race conditions that could have happened during these swaps. So we want a stronger statement than this frame statement. We want to claim that this function doesn't actually ever touch the memory that it doesn't have any business knowing about. Here we arrive to the notion of separation logic. And separation logic is the logic that, besides the usual connectives and or and implication and the logical quantifiers, also introduces separating conjunction and this operator that the authors of Iris call the magic wand. I don't know how established this term is, so I'll just be using it. And also separation logic doesn't only describe true statements, it instead specifies ownership of resources. In this context, the new connective that is called separating conjunction means that we own two resources, X and Y, separately, whereas X and Y means that we own a resource that can be interpreted as X and can be interpreted as y. X or y means that someone owns either X or Y. Implication of Y from X means that if a resource satisfies X, it will also satisfy Y. And the magic wand means that if this magic wand is merged with a resource that satisfies X, it will produce a resource that satisfies Y. Also, separation logic usually historically introduced a built-in notion of the heap and a new connective that is called points to. To the left is the memory location, and to the right is the value in this memory location. And this whole statement means the ownership of this memory location where the value v is present currently. This resource is exclusive, so if someone claims that they own L points to V1, and maybe someone else claims that they own L points to V2, then it is impossible. Only one such ownership statement can exist at the same time for each memory location. And here just to eradicate any possibility of confusion with the syntax are some operations that can be done on memory locations in terms of their specifications as Hoare triples. For example, we can allocate a new memory location that initially stores v, and then this execution of this statement will give the caller the ownership of some new memory location with the value v. Here I use this star as the dereferencing operator. So if someone owns the knowledge that L points to v, then reading from L returns returns that v, and also gives back the ownership, because we can read a variable more than once. Here are the definitions, the specifications for storing a variable value and for concurrent set. Any questions at this point? Someone has written something. Mikhail raised the hand. Yes, Mikhail?
Excuse me. And what does dot means? What does dot mean in this notation?
The dot means that the value returned by the statement S will be called v when given a specification in the post condition Q. For example, the simple expression free will return some v about which we know that it is equal to 3.
Okay, thank you.
Okay. Any other questions?
So for the dereferencing rule, is it important that we have here a separating conjunction? Can we replace it with usual conjunction here?
Here it is not at all important.
Mhm.
These are persistent statements. I didn't yet define what persistent statements are. And for persistent statements, like this one, this is not a persistent statement. It doesn't matter how you connect them to their neighbors.
Okay, thanks.
So I'll continue. When we operate with the separation logic that I just now showed, we can achieve a more elegant proof of quicksort that doesn't at all concern the parts of the array that are not touched by the quicksort. Here we can see some elaborate statements of ownership of the heap memory allocations. I use this notation where a part of an array maps to some list to mean that the memory cells of this array map to the elements of that list. So when I write here that the part of the array from starting from index called low and ending at index p-1 maps to the list LL, it means just this. Well, we didn't really win much, and now we have to explicitly state all the ownership. And also, as it turns out, the separation logic, as I've shown it, is not really sufficient to prove the concurrent version. Why is it not sufficient? It's not sufficient because we must somehow encode that if the variable finished is true, then the main thread should be able to get back the ownership of the subarray that it has sent for processing to another thread. And we don't really yet have any means of communication between threads. So what do we do? There are many iterations on the separation logic before Iris, and some of them could already deal with this particular issue that I've shown by using the notion of invariance, but we won't be covering those. Instead, we will look at how Iris would deal with this issue. First, some preliminary definitions. We need to look at the logical modalities that Iris uses. First, it uses what it calls the later modality. That is written as an empty triangle and means that the statement under that modality will be available as a resource one execution step later. This may be an obscure notion initially, but it is immensely important in cases where you have to store some invariance inside the others, where you have to store Hoare triples inside invariance, which is quite fancy for most people. So it is unlikely that you will encounter the later modality in proofs directly if you use Iris. However, there is one place where you will for sure encounter the later modality, and it is in the notion of unbounded recursion or loops that may spin forever. And the mechanism that deals with those is called the loop induction. Its statement is written here, and it says that if you want to prove B knowing A, then it is sufficient to prove B knowing A and assuming that B will already be true 1 moment later at time. 1 moment later in time. In practice, this means that if you want to prove that some function, maybe recursive function, maybe some function that awaits for some value to become true, permits the following specification, then you can assume that the recursive calls of that function do also permit the specification that you are trying to prove. This may look like a very strong statement, and if you want stronger guarantees, for example, if you want your programs to always terminate, then it is possible also to encode in Iris using the total versions of hard triples, but we won't be covering those. And we, in fact, will have to use this rule to prove the concurrent version of the quick sort algorithm. Another modality that we have to look at is called the persistence modality. If we have a resource P, then the empty white square P, read as always P, is a claim that P is persistent. What does it mean for a statement to be persistent? It means that if we managed to observe P as true at least once, then it can't possibly ever become false again. Next, we will discuss the general idea on which the Iris framework is built. The idea is as follows. It consists of the following points. Each running thread owns some resources. The user of Iris can define their own notion of resources as long as these resources satisfy the laws of resource algebras, which are in fact partial commutative semi-groups with some additional restrictions that we'll have a look at. These resources, for example, the points to connective that we already saw is one such resource. But in fact, almost everything that you can put in a hard triple in Iris is a resource. Next, the system itself, that is not some particular thread, but the system as a whole, is also permitted to own some resources. They are called invariant, and invariants are persistent. Once you give up from some thread the resources that it owns to an invariant, these resources stay invariant until the end of your program execution. This is done so that any thread can rely on invariance without bothering to check if the invariant is no longer valid due to actions by some other threads, which is a recurrent theme in the design of Iris. Threads don't really have the ability to interfere with one another, as opposed to some temporal logics like TLA, which forces one to specify the system as a whole. As opposed to that, Iris is heavily modular. You can specify the behavior of different operations without considering how these operations correlate with each other. As long as you define the invariance of the system as a whole suitably. The threads can use the resources stored in invariance as long as they take the proper care that at most one execution step later, the invariance will once again hold. So no other thread will be able to detect that the invariants were at some time violated. Here's a footnote that says that if you want to deal with weak memory models, it is possible with some modifications of Iris, but not Iris itself. And the final point here is that some resources are intentionally impossible to obtain, which will be used in proofs. This may look really obscure as of now, until we look at some examples. So let us proceed for now until the first example, dealing with the necessary definitions, after which I hope everything will become clear. Now, what are the resource algebras? Resource algebra is a commutative semigroup with the additional operations. Operations that is written like taking an absolute value when applied to resource algebras returns the core of the element, whatever it means. And this operation nu of A is a proposition that is only true if A is a valid resource. As I said, some resources are intentionally impossible to obtain, and these resources are exactly the invalid resources. Some additional requirements that may shed some light on the definitions of cores and validity. If something has a core, then the core of that core is the core of the element itself. Also, if an element has a core, then combining that element with its core via the semigroup operation, I will be using this central dot to mean the semigroup operation, equals to the element itself. Next, if we know that the composition of some resources is valid, then each resource on its own is also valid. And finally, the monotonicity requirement of the core. If an element has a core and that element is part of some larger resource, then the larger resource also has a core that can be represented as the composition of the core of A with some other element. And another not that important definition is that a resource algebra is unital if it's a monoid. We call its unit epsilon. Its core is itself, and we say that the monoidal unit is valid. Now, that's a bunch of definitions. Let's try to acquire some intuition behind them. What is the core? A core is the eternal part of the ownership. If some part of a known resource has a core, then ownership of the core is persistent. We can take a look at the definition to ensure that it does make sense. If someone owns an A, then it owns an A and also owns the core of A. If someone owns the core of A, then because of this rule, someone owns two copies of the core of A, or 3 copies, or really arbitrary many copies. So these copies can be freely shared among all the threads. They can be put in invariants. In fact, the persistent propositions are those that deny the usual concept of ownership. They are not owned by anyone as long as they are ever observed as true. Anyone can use them. It is customary to use the cores of some resources to encode some observed states of the data structure as a whole, along with its invariants. It may provide enough of a context to successfully deduce the state of the system as a whole. Now, the intuition behind validity can be probably shown with this example. Internally in Iris, the points to connective is implemented as just another resource. And as I've said earlier, each points to statement is mutually exclusive with another points to statement on the same memory location, and it is implemented as the composition of these 2 resources being an invalid resource. So the notion of validity gives us ways to define which states of the system as a whole can never be entered. Do the definitions related to the resource algebra make sense, or don't they?
Makes sense.
Makes sense. Great. I'll assume that they do, and we'll proceed with the examples, which may solidify the understanding. A simple resource algebra is the exclusive resource algebra parameterized by some arbitrary type of data structures. What are the elements of this resource algebra? They can be of 2 forms. One element is a dedicated element that denotes the invalid resources, and another is a constructor with 1 parameter that signifies the exclusive ownership of this value. Why is this called exclusive? It's because there can't be really 2 different instances of an exclusive resource. If we have 1 exclusive resource and we have another exclusive resource, then their composition always results in the invalid value. The notion of validity supports it. An exclusive resource is only valid if it is not the dedicated invalid value. And it should come as no surprise that there is no core of any element of the exclusive resource algebra. Another example is the sum resource algebra. If we have two resource algebras, X and Y, then we can define their sum as follows. The sum can be constructed in three ways. It can be constructed invalidly, it can contain an instance of X, or it can contain an instance of Y. The valid values of this resource algebra look like this. The invalid value is invalid. If the sum wraps a value X of a resource algebra X, then the whole sum is only valid if the wrapped value is valid, and ditto for Y. Now, how does composition work? Composition works as follows. Two sums that wrap values on the left hand can be composed, and the result is a wrapped value on the left hand. Two values on the right hand can be combined into a value on the right hand. If you attempt to combine a left hand value with a right hand value, or combine something with an invalid value, then the result is an invalid value. Also, the cores are defined, I'd say, somewhat intuitively. The wrapper is ignored. It does not interfere with the notion of a core of the thing that it wraps. So these are a couple of resources that we are going to need in order to prove the concurrent quicksort. Some notes about how the resources are used. At any point of execution of the program, you can choose to allocate any valid resource. When you allocate a resource, it is given a fresh name that is out of your control, and only the resources with the same name can ever be combined. So if you do allocate a resource at one point in the program, then you cannot reallocate and use the same resource. You can't really modify this resource via the allocation procedure. Instead, if you want to update the resource that you already own, you have to go through a frame-preserving update. What is a frame? A frame is a set of resources that exist somewhere, but not used for the operation of the frame-preserving update. For example, we could say that the ugly statement in the naive quicksort proof that had this form is the frame of the quicksort in that example. That is, these are the statements, the ownership instances that are not actually used by the operation. A frame-preserving update is an update that ensures that no matter what frame exists somewhere in the program, the result will be able to combine with them correctly to form a valid resource. This once again underlines the point of threads not being able to interfere with one another in iris. Another notion that we'll need to perform the proof is the invariance. We will denote the invariance in this way. This says that the resource R is owned by the system under the name N. What are the invariants and how can one use them? If you want to prove some specification for a particular program, and you also know that there is an invariant governing the behavior of the program as a whole, then you can instead opt to prove this statement if the program is atomic. That is, it is represented by an atomic operation. What does this say? This says that we will be able to use in the proof of this operation the knowledge that the resource R will be available at some later point in time, which once again is usually not important unless your resource is some arbitrary statement where an invariant is stored inside an invariant. You don't really have to be concerned about this. You can just remove the triangle with no harm. And in addition to proving the Q, you will also have to give back the resource that you took from the invariant by the end of the atomic operation, which is represented by also having to prove this. Another rule is that two invariants with the same name can be opened simultaneously. This is an intuitively a robust rule. Let's imagine that there is an invariant that owns some exclusive resource, like a points to connective. And if we could open the same invariant twice, then we would be able to derive falsehood from the fact that we would now obtain two copies of a points to connective. And the third rule is that at any point where you own the resource R, you can choose to put it into an invariant with an arbitrary name that you choose. So if you want to prove this thing, you can instead choose to prove this one. Do the invariants make sense? No questions here. Great. Someone raised a hand. Yes? Mikhail?
Could you show some examples of invariants?
Sure. That's what the next section is for. Here I will show some examples. Okay, I will proceed to the example then. Here I took the interesting part of the concurrent quicksort implementation, and I aim to prove it. What I'm interested in is the part after the partitioning part of the quicksort is performed. We allocate a new variable on which the threads will synchronize. I fork off the calculation of one of the recursive calls. and I signal that this thread has finished by setting the finished variable to true. And in the meantime, in the main thread, I proceed to run its own recursive call, and then I did write this out more elaborately than I did initially for illustrative purposes. Here we await until the other thread signals that it is done. So what do we know initially? We know initially that the part of the array that will be passed to one of the recursive calls contains some list L1. We are not interested in what that is for this particular part of the proof. Another part of the array contains the list L2. The partitioning value is B. We know how these values in these two lists relate to B. And here are the two things that we did not yet see in a proof. Here's some invariant, and here is some resource of ownership. So, as a first step, I allocate a new resource. I use the exclusive resource algebra, and I put a unit into it. This is a valid value, as any exclusive resource is valid. And Iris allocates the name gamma for me as the name of this resource. Next, I allocate an invariant that I will call n. And this is the statement of this invariant that can be true for two reasons. One reason could be this elaborate statement. The other one possibility for why this invariant holds is that the finished variable contains false. Initially, this invariant holds specifically because the finished variable contains false. What about this part? This part claims that if the finished variable contains true, then one of two things must be true. One possibility is that the system owns the exclusive resource that I just allocated. Another possibility is that the system owns the knowledge that the array part passed into the concurrent recursive call contains the sorted list L1. Here I used an ellipsis to denote the value of the invariant. Everywhere where you see an ellipsis, you should understand it to mean this. So initially, I don't put the resource that I allocated into an invariant. I will just hold it for now, and in fact, it will be owned by the main thread. I'm about to give a general outline of the proof. When the forked thread writes the true value into the finished variable, it moves from this state of the system as a whole to this state. At a later point, when the main thread looks into the finished variable and observes that it contains the true value, it knows that it is because the forked off thread put this in there. And so the main thread may provide its resource that it has a hold on, and take this thing instead and proceed as if there was no forked off thread. So let's look at why the behavior of the forked off part is sensible. Initially, we only pass the relevant knowledge needed for the recursive call and the invariant to the forked off thread. It just doesn't need anything else. Then, before writing the value true to the finished variable, which we assume to be an atomic operation because we don't deal with weak memory models here, we can open an invariant and close it after writing the value to the finished variable. Opening an invariant, we acquire this resource for use as we see fit. And how could this resource be formed? It could be formed by this possibility, which we, outside of this logic, do know to be true. We do know that initially this is why the invariant was true at the point where we opened it. However, inside the logic, because the separation logic of Iris does not deal with the system as a whole, we immediately forget the reason why this invariant holds. Maybe some other thread, for example, the main thread, did do something with it. So we can't really rule out this possibility. However, it doesn't bother us. If we, in this thread, think that the finished variable contained true, then this is a null operation, and we simply take out this permit and place the knowledge that our sublist was sorted instead. We, in any case, close the invariant using this possibility. Whereas this possibility can be proven to be impossible because we are the ones who own this statement, and heap ownership is exclusive. Any questions about the behavior of the forked off thread? I'll continue then to the main thread. What happens in the main thread? The main thread owns everything that it needs to own in order to prove quick sort. It also owns the exclusive unit value, and it remembers the invariant that it needs in order to communicate with the forked off thread. Here behind the scenes, we use lob induction, as otherwise we wouldn't be able to run this line. We wouldn't be able to have an infinite loop at all. Here we can rewrite the infinite loop as unbounded recursion, which is exactly what loop induction deals with. In each iteration of the loop, which potentially may never really finish, we do know that it will finish, as we do know that quicksort does finish eventually. But the proof would still proceed as normal if the other thread, the forked off thread, decided not to do anything at all, not to signal that it has finished, which is a limitation taken by the authors of Iris intentionally to be able to support algorithms other than weight-free ones. And once again, if you want to prove the totality, you will be able to do so, just not with the things that I show here. In each iteration, we read the value of the finished variable that is shared among threads. It is possible that we observe the value to be false. Just a second, please. Let me turn the lights on. That's better. We could have observed that the finished variable contains the false value, in which case we simply close the invariant without changing it. The only thing that opening the invariant allowed us is reading the variable value. As you may remember, we are unable to read the value of a variable unless we somehow obtain the exclusive ownership of the heap location that it inhabits. Another possibility that we could have observed is this one. Well, actually, we couldn't have, because we are the ones that own the exclusive unit. And if the system claims that it owns the exclusive unit by the same name, then it must be wrong. So by combining this exclusive unit with our exclusive unit, we can obtain an invalid value and prove that this branch is impossible. And the possibility that we are interested in is that the forked off thread already wrote true to the finished variable and already placed the ownership of its part of the array into the invariant. In which case, we take out this thing and instead of it place our thing, closing the invariant with this possibility. If the finished value was read to be true, then we may safely return. Why can we do that? Because by case analysis, we can prove this statement. Either the red value was false, in which case we loop back, in which case we have to provide all these resources, which luckily we have. Or we have read the true value and we can take out the knowledge that the other thread has finished with its part of the array. And so after this loop, we can proceed as usual in proving the quicksort specification. Questions about the example? No questions. I may proceed. Great. Now I'd like to show you some more elaborate resources because I somewhat intentionally chose a simple example of quicksort to be able to avoid spending too much time in the minutiae of resource manipulation. But in fact, Iris provides a huge wealth of resources. Let me demonstrate this by showing you the Iris source code. This is the Iris source code, and these are the files that contain the resource algebras. As you can see, there are quite a lot. And in fact, in some of these files, there are more than one resource defined. So there's a huge wealth of them. I won't cover nearly enough of them, but I will cover some of them. In particular, I'm interested in showing you the authoritative resource algebra, without which no serious proof of an elaborate concurrent data structure is ever written, as far as I saw. So let's begin. Some simple, really simple resources. The natural number resource algebra and the positive number resource algebra. They are defined with their semi-group operation being the plus. Each element is valid, and the core of the natural numbers is 0. And there can't be really any core of any positive number in regards to addition, because of this requirement. If we set the semi-group operation to be plus, then due to the fact that there is no unit for plus in positive numbers, this never holds in positive numbers. And for natural numbers, 0 is a suitable choice, the only suitable choice. So here's this. It's really not clear at the moment why we may ever need those, because these resources don't really ever interact in any interesting ways. If my thread owns, let's say, 5, and another thread owns, let's say, 7, what does it really give us? And if we recall the notion of frame preserving updates, then we can see that, in fact, allocating new values under the same resource name is perfectly valid. If the other thread owned, let's say, 7, and we owned 5 under the same name, then there exists a valid frame preserving update, after which we would own 12 and the other thread would still own 7. Given that each element is valid, every update is frame preserving. So why would we need those? And another resource algebra that leaves us with the same question, why would we need this one, is the resource algebra of natural numbers with the maximum. The elements are, once again, natural numbers. And as for the semi-group operation, we have the max operation. Each element is once again valid. And due to the idempotence of max, we can set the core of each value to be itself. Once again, no non-trivial interactions. And now enter the authoritative resource algebra. The authoritative resource algebra contains some really obscure elements that we won't explicitly define, as this would, in my opinion, obscure its purpose, and the authors of the IRIS framework seem to agree, as they did place the definition of the authoritative resource algebra long after they first used it. What does this resource algebra do? First, it is parameterized by a unital resource algebra, which is important. And here where we see E1, E2, some E. These are the elements of the resource algebra that the authoritative resource algebra is parameterized by. Okay. There are two types of elements of the authoritative resource algebra. One type is written with a black circle, and another one is written with a white circle. The black circle one is called the authoritative ownership of the resource. And the white circle one is called the fragmentary ownership of that resource. The key moment of why the authoritative resource algebra is useful is written in red. So let's go by these points. The elements of the authoritative resource algebra are either invalid or purely fragmentary, or they contain the authoritative piece as well. If our element contains an authoritative piece, as well as a fragmentary piece optionally, then this element is valid as long as both of these wrapped elements are valid, and the fragmentary element is in some sense smaller than the authoritative element. This is a key point. In fact, the authoritative piece stores, in some sense, an upper bound on what a resource may be, whereas the fragmentary piece stores some piece of that whole value, and when all the pieces are combined, they should form this complete value. The fragmentary value itself is valid if it wraps a valid value. Combining two authoritative pieces is invalid. If you ever see in a proof two authoritative pieces, it means something went wrong, because, as you can guess, there can only be one authoritative piece. There can only be one whole of which the other pieces are fragments. And the fragments, on the other hand, can be combined together to form a combined fragmentary pieces. This equality works both ways. So if you have a fragmentary piece, you can split it in several. The core of the authoritative piece doesn't exist, and the core of the fragmentary piece is the core of the piece itself, placed as a fragment. Here are some examples. If we state that the system, for example, owns 2 as a natural number in the authoritative sense, then there can be at most 2 instances of fragmentary ownership of the number 1. So if you have an invariant somewhere and you want to give no more than, say, 2 threads permits to do something, you can encode it using the authoritative resource algebra along with the natural number resource algebra. And the structure of the authoritative resource algebra will ensure that you won't have too many permits, too many threads running in parallel where they shouldn't. Another example is that if you store in your authoritative resource algebra a maximal number resource algebra instance, let's say n, and you have a fragment that stores the number 2, then you can be sure that that n will be larger than 1. It will be at least 2. This is often used to encode the progress of the system. If your system works in several stages, you can use this fragmentary piece to always know when opening the invariant that the authoritative piece will contain an n of at least 2. So here is what I wanted to show you about the authoritative resource algebra. Do you now have some understanding of what it is, or are there any questions? No questions, I will proceed. Great. At this point, I have talked at length about how proofs are structured in Iris, but I'm yet to tell you proofs of what Iris can provide. For example, I've used some pseudo Python to describe the proofs that can be possible to make in Iris, but surely Iris does not actually work with Python. And in fact, the only reason why it can't is because Python is too boring of a concurrent language to have any non-trivial behavior that would warrant such heavy machinery. Because Iris, as the title of the slide says, is generic, which means that Iris is really simple, compact logic that doesn't actually encode anything about the languages that it works with. Iris does come with a sample language called heaplang, and you would be hard-pressed in practice to find any proofs involving Iris that were not done with the heaplang. But in theory, you could use Iris as is. You could take their whole calc formalization and with a few simple, from the point of view of Iris definitions, you could make Iris supported. I wanted at this point to show you how the Hoare triples are defined in Iris and how the notion of the weakest precondition upon which the Hoare triples notion is built is defined in Iris. Here's an unfortunate typo. Let me just fix it really quickly. And yeah, fixed. How are Horde triples defined? The Horde triples in Iris are defined as follows. We say that the Horde triple holds true if we can persistently state that it is sufficient to establish P to know that to have the weakest precondition of the program E returning a value V that obeys Q. Now, what is the weakest precondition? The weakest precondition is the resource required for the program to run successfully, as opposed to hang in the bad sense. That is, exhibit some undefined behavior, and infinite loops are fine. And if it ever finishes with the value V, to have Q hold afterwards. Here's a sample program. We read from the X, we read from the Y, we subtract the results, we compare them to 0, and we want the result to be true. This resource is equivalent to this one. This will only be true if this holds. That is, we own some X that points to some A, we own a Y that points to some B, and A is greater than B. But in fact, this statement does not reduce to this one. It reduces to something else entirely. And here I will show you the beginning of the document called Iris from the ground up, section 6.3 that discusses the weakest preconditions. And I will be done with the slides. Here are some references. If you want to study Iris on your own, this will probably be enough. It was enough for me. So let's move to the official documentation. The point of which is really just to show you how simple this definition of the weakest precondition is internally, and how little is actually required to be able to support another language. Why and when does the weakest precondition hold? It holds in two cases. One case is when the program is itself a value, and we don't really have any ability to reduce it further. Then, in order to show the weakest precondition, we have to show that this property holds on the result. The other possibility is that the program is not a value. Can it then be reduced? A big question. The cases where it can't be reduced are, in fact, the undefined behavior cases. If it can be reduced, and if the program E using the heap sigma reduces to another program E2 with the heap sigma 2, and we'll ignore the forked off threads for now, then it will be sufficient to show that the weakest precondition for the program that this one reduced to with the same post condition also holds. Now, this gives a fairly accurate understanding of what one must implement to have their language supported by Iris. That is, these two things. the notion of when something is reducible, and the notion of where the program will be reduced to. This notion is heavily simplified as opposed to the actual notion of the weakest precondition, which looks like this. It has this new modality that I didn't discuss, but so we can't really hope to understand this in full. But here we can see that the heap is not really some magical thing. The program heap is just another resource, an authoritative one, and the points to connective is implemented as a fragment of that heap resource. If you are interested specifically in what all of this means, I heavily recommend that you read this document. It is beginner-friendly, not a complete beginner-friendly. For that, I would recommend the IRIS tutorial. But if you have some solid understanding of what separation logic is, then this document is the way to go. And finally, I wanted to show you how the proof mode of IRIS, what the proof mode of IRIS in Coq looks like. I assume that everyone in the attendance has seen Coq and probably has an idea about what's happening on the screen. So here are the program definitions written in heap lang. Rec is the operator that defines new recursive functions with this name and these arguments. The exclamation sign is the operator for reading from memory locations. The ref command is an operator that allocates new memory locations. Concurrent set we have here assignments. So these are just the program definitions. Then one has to list the resource algebras that one would like to use. These definitions are really obscure, and I did manage to write fairly competent IRIS for nearly a year before understanding what these things mean. So I just copy-pasted those. The crux of them is here. You want to list the resource algebras that you use in these statements in this form. For example, here we have an authoritative resource algebra that is parameterized by a product unitary resource algebra that is parameterized by two other resource algebras. Here we have a definition of an invariant. The file that I'm looking at is a ticket log. We won't be able to cover what a ticket log is in the remaining 5 minutes. But you may be able to see that this looks much like plain Coq. There are no strange string literals. In fact, there are, but they are hidden from your view. Here are some definitions of tokens used throughout the proof. Here is an example of a token that establishes the ownership of a fragmentary piece of an authoritative resource algebra, where the piece looks like a pair of a unit and some singleton set. Then let's step inside one of the proofs. Let's say we want to prove a Hoare triple of this form. The comments starting with I are comments that belong to Iris, and they enter a mode called Iris mode. Here you can see the plain COC context, and here you can see the Iris context. Here we have just the usual logical propositions, and here we have the statements of ownership of resources. And the illusion that we were dealing with hard triples quickly came to an end, because immediately the Iris mode forces us to work with the weakest preconditions. Some modalities. Comments that start with WP mean that these are comments related to weakest preconditions, so they perform some reduction steps. For example, we know that new lock is a lambda, and a unit is passed to it. So the command vplem reduces it to the definition. Then the command vpalloc is performed, which allocates a new fragmentary piece of the global heap resource. Here I wanted to show you another piece of the context. We thought that we had two contexts, one COC context and another resource ownership context. But we have, in fact, another context of persistent propositions. Here, an invariant was placed there. And I think that's it. Does anyone have any questions before we finish? No questions then, correct? Well, thank you all for coming. And with that, my talk concludes.
Does anybody have questions?
Thanks for the talk. Could you please go back to the slide with the footnote about weak memory models?
Slide about the weak memory models. There wasn't much written there about the weak memory models. You're interested in something else on that slide?
No, I was about to ask about the footnote, because from the context it follows that the implementation of weak memory models in Iris doesn't follow the invariant principle, or maybe I didn't understand. What did you say here?
What I said is that when we don't have a weak memory model, when we assume strong memory model, we can assume that one execution step performed by any thread is in fact enough for the other threads to observe the changes that this thread produced.
Okay.
So if we wanted to work in weak memory models, we wouldn't have such an easy to define and such strong notion of invariance, because we would not only have to close them immediately after one execution step, we would also have to either make sure that the operation we performed was under the memory barrier, so the other threads immediately see its results, or we would have to actually take care to observe that the other threads are not going to observe the changes that we made in the wrong order, thus violating the invariance we have.
Okay, so as far as I understand, it reduces to immediately eliminating the effect of weak memory, as I understand. That is...
in Iris, we assume that any changes to the memory are immediate and always seen by everyone else.
Okay, thanks.
More questions, please? Well, then I have. You say that you developed the familiarity with the framework after 1 year. Is it?
Yeah, I did.
So it's but I. So is this the common case? Is this here would be required for everyone else? So does this framework require 1 year of dense work to develop the familiarity? What is your estimation for everyone else?
Well, I don't know everyone else, naturally. I would assume that it would take much less than a year of some directed effort. My problem was primarily that I didn't really know where to look. But now that I have learned about the Iris framework, everything that I was feasibly going to, I know that it would be enough for me to read the Iris from the ground up and the Iris lecture notes, which could conceivably be done in about a month. And this could potentially be shortened further by having a mentor who already knows something about Iris. My problem was that I was working with Iris in an industrial context of proving some real code, not for academia, but for the industry. And there wasn't really any initiative to sit down and learn everything. I, at any point of time, needed to learn just enough to keep my proofs going. So I'd say about a month, not now that I've told you where to look, and maybe a week, a couple of weeks, if you have a competent person alongside you who has already worked through it.
So now when we have you, this time would be shortened sufficiently, right?
Sure. If anyone would like to learn Iris, feel free to reach out. I may sit down with you, and we may work through your issues together.
And another question: how did you come up to know Iris? What was it concerned with your job, or it was your initiative to start learning these things? And who asked you to prove anything concurrent? Actually,
It's just an accident, I suppose. After I graduated from the university, I was looking for a job, and I went to the Kotlin coroutines team because I just was interested in concurrency in general. I assumed that we would be doing some high performance work, but now that I do work in the coroutines team, I can tell you that we are not. We are mostly busy designing APIs for people to use. But nonetheless, there were some internships open, and I applied. The mentor of my internship, Nikita Koval, has asked me about my background, to which I answered about my diploma, which concerned proof assistance. And it turns out that Nikita has been eager for a long time to get his hands on a formal proof of some of his data structures. So he saw that as an opportunity, and I wasn't really against it. It seemed like a fun endeavor. About half a year later, it sort of became tedious, but in the end, I persevered and succeeded.
did you prove the correctness of those structures, or did you discover some errors in the implementation?
Both.
Okay. Does anybody else have any questions for our presenter? Well, to me, it looks quite hardcore to be true, to say the truth, but it was very interesting. I presume
It looked quite what?
Hardcore.
Sorry, hardcore.
Yeah, complicated. It's hard stuff to me. Well, everything which concerns verification looks hard for me actually. So. No
well,
question.
I was told that people here are mostly interested in the internals, in all the nitty-gritty details. Otherwise, I would probably do something like a demo with some user visible features as a focus.
I presume, yeah, well, we have here an audience who might be interested in the details and the implementation, etc. So I am a little surprised that not so much questions came up. So I expected the waterfall questions actually, but nevertheless, if nobody else has any questions, let's conclude your talk, which was very interesting, and I presume now we know how to look if we want to prove formally, certified in a certified way, prove something about concurrent data structures. Yet another framework to do the job. So thank you very much for your talk, and perhaps
you're welcome.
Thank you. See you some other time as well.
Goodbye.
Bye bye.
Thank you. Bye.
Thanks. Bye.
Thank you.